Good morning, friends. Myself, Dr. Kushal Bhattacharya. Today, I should be discussing another important topics in mechanical engineering related to fatigue loading. So, the previous lecture in fatigue loading, I have discussed what is high cycle fatigue and low cycle fatigue, and I have discussed for completely reversal load. Now, today, I should be discussing about the Goodman diagram and the Soderberg diagram. And these are the two important the Soderberg criteria and the Goodman criteria. These are the two important criteria for fatigue loading, where mean stress and amplitude both are present. Now, how to deal with that sort of problems, I should be discussing today. First, concentrate on the board. So first, we have seen that what are the types of loading. So we have seen that basically we have seen that this is one criteria of load. This is one criteria of load where we find that this is a sigma amplitude, sigma A, and the mean component of the stress, the mean stress, that is the sigma M. The sigma M is 0. Why sigma M is 0? Because sigma mean is basically sigma plus positive sigma max plus sigma mean. This is minimum by 0. Now what happens? This sigma max minus sigma minimum, so these two are same. Sigma max is equals to sigma minimum plus sigma max is equal to minus sigma max. So plus sigma max and minus sigma max, because this one and this one are same. So this amount of this is the amount of peak stress sigma max positive and sigma max negative, because this is the, if you consider this is the zero line, this is the tension and this is the compression side. So what happens? Sigma max minus sigma mean is equals to 0. So this where sigma mean is 0, but sigma amplitude is there. What is basically simple sigma amplitude? We have known that sigma amplitude is basically, I'm just recapitulating what we have done. Sigma amplitude is basically sigma max minus sigma mean by 2. Now what happened over here is important. Sigma mean is same sign but opposite sign, minus, so it becomes 2 sigma max. So ultimately it becomes minus minus plus, so it becomes sigma max by 2. So it becomes sigma max. This amplitude is equal to sigma max, or say this amplitude is sigma max. So this is one criteria. Then for that we have gone for the SN curve. If you remember, we have SN curve, and we have find out the endurance strength of the material. So that has been discussed previously. Now, if there are some certain case of loadings are there are certain cases of loading are there where we get both the component of sigma M and sigma A. So if you see this sort of components, if you see, if I plot the value of time over here, and if I plot the value of sigma, we shown that there are some type of loadings are there. There are certain types of loadings are there which looks like this. This is repeating stress. Where what happened? I have discussed in the first lecture. So here we got a value of sigma maximum. Here we have got a value of sigma minimum. Here, if you see both. Here, if you see both things are present. Here, if you see sigma amplitude, this is sigma amplitude. Sigma A is there. This is sigma A is there, and sigma mean is there. Both things are there. Sigma mean over here, sigma mean is equals to what over here? Sigma max plus sigma mean. Sigma max plus sigma mean. So if I write like this, if you can see from here, if I write like this, sigma mean is equals to sigma max plus sigma mean by 2. That is, it is this sigma mean is present, and if I go for sigma amplitude, sigma A, so here we also get sigma max minus sigma mean by 2. So over here this component sigma mean is there. If you see this figure, this component sigma mean is there. If you see this sigma mean, here sigma mean is also there. So now an important understanding is that this sort of condition, if you want to deal with this sort of criteria, then what should be the criteria? Because you cannot say, because in this sort of figure, you cannot say in this sort of figures, if it is as this component is present, you cannot omit this component. Previously for SN curve, on where sigma m is 0, if you go for SN curve, sigma m is 0 for SN curve, but where sigma a and sigma m both are present, then what should be the diagram or what should be the design criteria? Basically, what should be the design criteria for this sort of loadings? Because here the design criteria is endurance strength for SN curve. We know the design criteria is endurance strength, we have discussed, and now for static loading, the design criteria is yield stress or ultimate stress. But for certain kind of fatigue loading where mean and amplitude both stresses are present, what should be the design criteria for that sort of design? Now for that reason, we done a plot over here. If you concentrate on this plot, we done a plot over here. Now we do a plot over here, where we basically consider this axis, the x-axis, this is the y-axis, the x-axis or the abscissa, we take mean stress, we take the value of mean stress, positive mean stress, and this is negative mean stress. This is positive mean stress and this is negative mean stress. So now what happens? Positive mean stress means tension and negative mean stress means compression. So this is the two criteria I have taken. Now this is the abscissa, and the ordinate represents the amplitude. Because we have considered this sort of loading. I have told you once more, showing you once more. We have considered this sort of loading where both what happened, amplitude is also present and mean is also present and sigma mean is also present. So both components are present. As because both components are present, so if a force is like this, this is a value of stress. This varies with time. So if this is the condition, how to design that? Now basically what we do is an important criteria you see over here. If you see that if the amplitude, now if sigma a is 0, now if you consider for the shape sigma a is 0, sigma amplitude, there is no sigma amplitude, that means this amplitude, if you see this figure, this amplitude sigma a, this is basically sigma, this sigma is 0. If this sigma is 0, then what happened? This will become a straight line, this will become a straight line, this will become a straight line. That means it becomes a case of a static loading. That means the load or the force does not repeat itself with time. Now, so this should be the case of the static loading. Then the design criteria should be yield stress or ultimate stress. No problem. But over here, if you consider sigma, sigma a is 0, now what happened if sigma m is 0? If you consider sigma m is 0, if sigma m is 0, what will happen? It will take place for completely reversal load that we have seen, for completely reversal load, that is for completely reversal load where sigma mean is 0, and we should go for SN curve. And the design criteria is endurance strength. Now what happened where both type of loadings are applied, this condition where both type of loads are applied, that is where sigma a is not 0 and sigma mean is also not 0, then what should be the design and how we should design this sort of how we design of the component which is made up of the material, and that component is subjected to both type of loading. What should be our design criteria? Based on what we should design. Now for this, an important thing is that, so we have seen that what are the two perspectives when this one is 0 and when this one is 0, what are the two perspectives. Now under this condition we perform the test for a component, and we calculate the number of cycles and we find out the values and we find out the failure values. We have given the applied load to it. We have given the applied load to it. And what happens where both sigma m and sigma a is present, and we have noted the failure points, and we are plotting these failure points. We are basically plotting these failure points. We basically plot these failure points. So we note what is the amplitude mean stress present and what amplitude stress the failure takes place, and we take certain value of the failure points. We take certain value of the failure points. We take certain value of the failure points, both for tension and both for compression. We take certain value of failure points. We take certain value of failure points. Because when a number of specimens are there, we perform a huge number of tests with the specimens both for tension and compression, and we have find it and we have plotted this. Now we know for if sigma m is 0, I have considered before also, if sigma m is 0, the failure criteria is endurance strength. So we are plotting endurance strength over here, sigma e. Now when sigma a is 0, the failure criteria is what? Sigma ultimate or sigma yield. Sigma ultimate stress or sigma yield stress. Now this is the conditions. We have plotted certain failure points. We have taken a lot of specimens and we have applied this repeated stress where both sigma m and sigma a is present, and we have plotted the diagram. Now what we do basically what we do is we do a curve fitting to it. We do a straight line curve fit to it, and on statement curve fitting, if we plot a straight curve to it, if we take from the endurance strength to ultimate strength, we join a curve both for tension and compression, and we join over here also because there is also an ultimate compressive stress and yields ultimate compressive stress UC, sigma UC and sigma y is yield stress. We plot two lines from here and from here. We plot two lines. Now basically we see that when we plot these two lines, what happens? This is basically a curve fit. Basically a curve fit, and because some engineers thought that this curve, that is joining from yield strength to ultimate strength, takes many number of points. Some things that no, this curve joining from endurance strength to yield strength takes many number of failure points. Now another way they fit a parabola to it. Another scientists, they fit a parabola to it. Now what happened? This is basically nothing but curve fitting. Those who have fitted the endurance strength with the yield ultimate strength, they are calling this curve as the Goodman criteria, Goodman diagram or Goodman criteria. And those who have considered that in endurance strength with yield strength, they are considering it as the Soderberg criteria. Soderberg criteria. And those who are considering this parabola, this is called a Gerber parabola. This is called a Gerber parabola. Gerber parabola. So this is basically the conditions of where both types of loads are applied. So Goodman criteria is maximally used because it is used in most designs where both actually endurance strength and yield strength is there, and some regions and some points and some considered Soderberg criteria. But Soderberg criteria, you think, it's a more conservative. It takes more conservative because it's more away from failure. So some considered as a Soderberg criteria as an important criteria for failure. Now we have rubbed this and we'll draw a fresh line from here. We'll draw a fresh line from here. And this curve, we know, represents the main stress, and this curve represents the amplitude stress. Now all failure points are there. I'm not drawing the failure points because it makes clumsy. And over here I consider the endurance strength, and over here I have considered the yield strength, and over here I have considered the ultimate strength. Now basically what happens, I'm drawing it. So this curve, this line, Soderberg thinks that the line joining the endurance strength and the yield strength will comprise more number of failure points, and Goodman considered that no, the line joining the endurance strength and the ultimate strength will capture the more failure points. This is only a curve fit, nothing else, I'm telling you. And Gerber thinks that no, the parabolic form will capture more the failure points, and they propose according to it. Apart from that, there is no difference. One difference you could see that if you consider yield point and the endurance point, you could only go for ductile failures, because brittle material there is no sharp defined yield points. So from this clarification, it is clear that Soderberg criteria can only apply for ductile material, no problem. And brittle material you have to go for the Goodman, because you have brittle material, there is no sharp defined yield point. So you, for brittle material, for brittle failure, you have to go for Goodman criteria. So that is that. Now I am taking the Soderberg as the failure criteria, and I am drawing a safe line. Now what is this? Basically the safe line. I am drawing a safe line from here. I am drawing a safe line. Now what is this safe line basically? What is this safe line basically? This safe line is basically what? Sigma yield, I am considering the Soderberg, by factor of safety Fs, and this line and this portion is considered sigma endurance by factor of safety. So this is both case, considering the Soderberg as my criteria, I have taken used the factor of safety. Factors of safety is the yield stress by the ultimate yield stress by working stress by ultimate stress. So we know this. From this we have taken, that is the factor of safety is basically we know that I am reminding also there is ultimate stress by working stress. So ultimate stress by working stress. So working stress becomes what? Ultimate stress by factor of safety. By factor of safety. Now over here what you could see, that factor of safety is equal to the ultimate stress by the working stress, or the yield stress by the working stress. Over here I have taken yield stress by the working stress. So I am just writing for Soderberg I have taken yield criteria. So so over here what happens? This is the working stress, sigma W, the working stress, the sigma W, the working stress becomes then what? Sigma ultimate by factor of safety, sigma ultimate by factor of safety, and sigma ultimate by working stress by factor of safety if it is for Goodman criteria, and working stress for Soderberg criteria is sigma yield by factor of safety. And I have done this, and I have written this sigma y by factor of safety, and for endurance strength also I have taken a factor of safety, and I am writing this sigma endurance by factor of safety. I am writing this. So that is the point. Now over here in this line I could do the drawing anywhere. I could consider my point of design anywhere. Suppose I have considered my point of design over here. If I consider my point of design over here, so what basically I will get? What basically I will get this region, which I may call as any name, sigma h, or sigma h, and I could give this as sigma vertical, sigma horizontal and sigma vertical. So sigma horizontal normally refers to mean stress, so I am writing this as sigma m. It represents the mean stress. So sigma m, and this is sigma vertical stress. Now what happened? Now basically I will now give some points over here, name OA. Now this is F, this is E, and this I will produce B, and this I will produce C, and this I will name as D. Now from this over here, from this diagram, we could write that EF, we could write that EF by FC EF by FC is equals to EF by FC is equals to AO by OB. AO by OB. We could write this from the similar triangles. We could write this, that EF by FC, if you consider triangle EFC similar to triangle OAB, considering similar triangles, triangle AEFC and similar triangle OA, similar triangle OAB. So we could write this, that is EF by FC by AO by AB. Now we write this. Now what happened? FE is basically what? Sigma V. And FC, what we could write? FC we could write like this. FC we could write like this. OB, FC we could write OB minus OF, OB minus OF. So in place of FC we could write this OB minus OC, OB minus OC. So we could write this OB minus OC, and this is AO by OB. Now what happened? If I write this sigma V OB, OB basically represent what? OB basically represent yield stress, that is sigma Y OB yield stress minus OC. OC is what? Sigma Y by factor of safety, and AO is equals to what? AO. AO is equals to what? AO is equals to the endurance strength of the material, and OB. OB is basically what? Endurance. Sigma is the AO is the endurance strength of the material, and again OB is the yield stress of the material. Now if I write like this, AB is the, now this is the equation, sigma V by sigma Y minus sigma Y by factor of safety by sigma E by sigma YF, sigma Y. So now what happens? If we rearrange this, we get like this: 1 by factor of safety is equals to 1 by factor of safety is equals to like this: 1 by factor of safety sigma M by sigma yield point plus sigma V by sigma endurance. Now this is the criteria for Soderberg line, taking the safe factor. So you can take any value of sigma V and sigma M. So, and because sigma yield point, sigma YP, the yield point, and sigma endurance is known for the material, so you can take any value of sigma M and sigma V if you consider Soderberg criteria as your safe design line. If you consider your Soderberg criteria as your safe design line. Now for Goodman criteria, everything will remain same, only the equation will changes a little bit, where 1 by factor of safety, it should become equals to sigma M by sigma ultimate. In similar way you could prove it, this should be sigma ultimate plus sigma V by sigma endurance strength. Similar way you could prove it from the help of a triangle. Now this is the equation, this is the basic, this is the equation, this is the criteria for Goodman diagram. So this is only, it will change for sigma ultimate, and some other things will remain the same. So you can choose your design criteria, anything, only here the safe line will change, here the safe line will go more towards this one, anything. But you could, for considering the endurance Soderberg criteria, you can take the point over here also, you can take the point over here also, depending the value of sigma M and sigma V, you can take anywhere over here, because it is a safe design criteria. Now up to this, I think that I have explained the Goodman diagram, the Soderberg diagram, and the Gerberparbola to the best as I know. So if you like my lecture, just put a thumb mark to it, and you could subscribe to my channel for more videos like this. Thank you. Have a good day.